We're going to do Chapter 4, number 26. In this problem, it looks like we have two packing crates of masses 10 kilograms and 5 kilograms are connected by a light string that passes over a frictionless pulley, as in figure P4.26. The 5 kilogram crate lies on a smooth incline of angle 40 degrees. Find the acceleration of the 5 kilogram crate and the tension in the spring. So we need to draw the situation that we have. We have this inclined plane. We are inclined at 40 degrees. So theta equals 40. We have two boxes. We have a 5 kilogram box sitting here. Box number 1. I guess I call that box number 2. So we're going to call that box number 2. And it carries over, goes over this frictionless pulley, and has this this other box hanging here. I call that one box 1. Mass of box number 1 is 10 kilograms. Mass of box number 2 is 5 kilograms. And are we given anything else? I think that's everything we have, right? And we're asked to find acceleration equals what? And tension is equal to what? Okay. There's a couple key points for these kinds of problems, these things that you have on kind of an incline when you have two different boxes. So you have a box sitting on the incline and a box that's hanging off the other side. You kind of fiddle with your coordinate system a little bit. Okay? So the x direction, it kind of follows the incline. So the x direction here is going to be along the incline, and then when you get over the incline, it's going to be up and down. Okay? So that's one of the key points to realize. You have to follow the incline and kind of trace the direction that the boxes are going to move. So you have this, all of this is going to be the x direction. And then the y direction is just going to be the y direction of this one block bouncing up and down, potentially on this incline. Okay? So the first step that we're going to do is to identify all the forces that are acting. So let's write down all the forces that are acting. What forces do I have acting on these boxes? Box number 1, let's do first. Gravity? Where does gravity act? Gravity is acting downward. So we'll call that Fg1. Force of gravity on the first box, and that's going to be equal to what? Mass 1 times acceleration of gravity. Okay? Mg. Any other forces acting on it? Natural force? Is it sitting on anything? Nope, so no natural force. What else? No normal, no natural force, normal force. Tension? Where's tension? It's a string. Okay, so tension is kind of acting in this little rope, acting up. Tension on the first box. Anything else? No? Okay, let's look at the second box. What forces are acting on the second box? Normal force? Where does the normal force act? Perpendicular to the surface, so our normal force, there's our F in force. What other forces? Gravity? Where does gravity act? Down. Gravity, straight down. Force of gravity on the second block, and what's that going to be equal to? Mass of the second block times g. Okay? What other forces? Any other forces? Force of friction. Does it mention friction here? So what it says, we have a 5 kilogram crate lies on a smooth incline of angle 40 degrees. When they say smooth, that means no friction. Okay? If there is friction, then they will give you a coefficient due to friction, like problem 49. We'll come back to that. So no friction. Any other forces? Tension, where does tension go? Up the incline towards the pulley. Tension on box number 2. Okay. What do I have to do since I have this force that's acting down? It's kind of acting at an angle. What do you do anytime you see any force acting at any angle? Break it into x and y. So we have some little bit in the x direction, or in the y direction, and some little bit in the x direction. Yeah. So we have some FG. That's going to be box 2 in the y direction, and FG box 2 in the x direction. Yeah? Okay. So let's write out all of these forces. FG1 is equal to M1 times G. Tension 1, don't know what that is. There is something that we do know about tension 1, though. Tension 1 is equal to tension 2. This is another kind of tricky thing that you have to know in these kinds of problems. It's in the examples in your book where they point out that the tension in both parts of the string are the same. They both have the same amount of stretch that's being applied to them. The string down here isn't any less tight than the string down here. It's the same tension throughout the whole thing. Yeah. If the tension were different, then this part might be up above the incline a little bit more, might be a little bit higher. Then this tension wouldn't exist. As soon as you don't have a tension here equal to a tension here, the rope kind of catches up on itself. Yeah, it's not completely taut. So as long as your rope is completely taut, tension 1 is equal to tension 2. Okay, so they're the same tension, and I'll just call that tension equal to T. We can do FG2. FG2 is equal to M2 times G. What else? We have components, FG2 in the x direction. What is FG2 in the x direction? Right along here. It's the sine. So we remember our angle. This angle is theta. I'm on the opposite side. Opposite gives you sine. So FG2x should be M2G times sine of theta. FG2y is equal to what? It's going to be cosine. M2 times G times cosine. Okay. It's what? Yeah. Sorry, that's a 2. I have chicken scratch handwriting. 2. I don't know if that 2 is any better. It's like a Z or something. Okay. So, we know every single force that's acting on this now, right? It's a big fat mess, but we know all the forces. So what we can do, once we know all the forces acting on any box, for box number 1, right here, in the direction of sliding. So sliding direction is going to be up and down the incline, and then up and down vertically. So box number 1, which forces are acting in the sliding direction? FG1 and T1. Are they acting the same direction or different directions? Different directions. So I need to pick which direction I want to be positive and what direction I want to be negative. My tendency, I usually always do the same direction being positive. I usually always go with sliding up and down this way being the positive direction. That make sense? Okay. So which one of these forces is going to be positive? FG1 or T1? FG1. So I can write my sum. Box 2. Here we go. In the sliding direction. What forces do we have acting in the sliding direction? Along the incline. T2 is acting that way. Is T2 positive or negative? It's positive according to what we chose. Any other forces acting? Along this direction. FG2X. Okay, so FG2X is acting opposite, so FG2X is going to be negative. Where could I draw friction in here? Down the incline. So if I had friction, friction would be acting down this way. Okay, and where would that play in? Where would that be added? Which sum of forces? Box 1 or box 2? Box 2. Okay, and I just subtract off whatever the force of friction is. Okay, and that's how you do problem 49. It's the exact same approach. You just have to include friction. Yeah? Yeah. All right. For Newton's law problems, for identifying forces. What does Newton's second law say? Sum of forces is equal to the mass times the acceleration. Right? So that's Newton's second law. So we need to do that for this box. We need to do it for box 1. We need to do it for box 2. And we need to do it in different directions for each of them. So for box number 1, the sum of forces, and I'm going to call the direction the slide direction, the direction that we're sliding along. This is kind of like the x direction. Is going to be equal to, what is this going to be equal to for box number 1? Do we remember? We can go back to box number 1. Is going to be FG1 minus tension 1. And that's going to be equal to mass 1, the box that's actually talking about, times the acceleration of that first box. Whatever that box's acceleration is. That make sense? Now we can do the same thing for box number 2. Box 2. Sum of forces in the slide direction for box 2. Alright, let's go back and look at our... So, we can write that out. We have tension 2 was acting up, minus FG2X, and that's going to be equal to what? What mass are we talking about? Mass 2. And what's the acceleration? Acceleration of box 2. So we can write this out a little bit differently. Sum of forces in the slide direction for box 2 is equal to T2 minus M2 times G times sine of theta. And that's equal to M2 A2. Okay? Okay. So now we have to realize one last thing. We have to realize something about the accelerations. What do we have? Accelerations. Two boxes on an incline. Box 1, box 2. Let me say A1 is not equal to A2. Take it a step further, A1 is greater than A2. What happens if this box here is moving faster, accelerating faster than this box can keep up with it? What would happen? It's what? It's going to fall. But if it's falling faster than this box can keep up with, then it'll break the string. What if this is falling slower? What if this box is catching up to this one? What happens to the string then?
Won't it just stop?
The string isn't tight. There's no tension. So, A1, for this situation to work, for this whole problem to work, A1 has to be equal to A2. The accelerations have to be equal to each other. So tensions have to be equal and accelerations have to be equal. Those are the key points to remember in the problem. Okay? So once you realize this, you can write down your Newton's law equations that you have. You have M1 times A is equal to M1 times G minus tension. We'll call that equation number 1. And you have a second equation. You have an equation M2 times A is equal to T minus M2 times G times sine of theta. Now let's take stock of what we do and do not know. Do we know what M2 is? Were we given the mass? Yes? Yes. Do we know what A is? No, we have to find that. So we have to find A. Do we know what T is? No, we have to find T. M2? Yep, we know what that is. Do we know what G is? Yep. Do we know sine of theta? Yep. How about the first equation? Do we know M1? Yep, A. Well, we know A is the same in both of these, so we know these two are equal to each other. M1? Yep. G? Yep. Tension? Still need to find what tension is. So I have two equations. And how many things do I not know? 2. Can I solve them? Yes. 2 equations and 2 unknowns, you can solve for both of them. Okay? So that's all the physics. Do you need to see more than this? Do you need to see the solution all the way? No? Okay. So there you go. You will end up, once you find your acceleration will be equal to 4.43. And what are the units on that? Meters per second squared. And how about the tension? The tension will be equal to 53.7. And what are the units on that? Newtons. Any questions? I have only one question for you. What happens if there's friction? Can't hear you. Yeah, if they give you what that is, they would give you what the friction coefficient is. So what do? You subtract that from what? Where would friction be?